Hello, welcome to my electromagnetic fields project video. Today we will be discussing homopolar motors and how they work. To do this, I built several homopolar motors using 4 different designs. Regardless of the design, they all shared the same 3 components. A current source, represented here by a AA battery, a length of wire, and a magnet. Later, we will be adding a 4th component, but for now we'll keep it simple. A homopolar motor is simply a current-carrying wire turning in a magnetic field. For my first motor, I used a fairly standard design. The wire wraps from the positive terminal of the battery to the magnet that is attached to the negative terminal, completing the circuit and allowing a current to flow through the wire from positive to negative. The magnet produces a magnetic field that encounters the wire moving in this direction. That is all we need. From this point, the wire should begin to spin. This motion is defined by a law of physics known as the Lorentz Force. The Lorentz Force is an equation built of 2 parts: the force due to an electric field and the force due to a magnetic field. Now, for our purposes today, we will focus on the magnetic field instead of the electric field. Now let's look at what this equation is saying. The force due to a magnetic field is equal to a charge with some velocity crossed with a magnetic field. If we interpret that a bit, we can remember that a charge with velocity is a current. We can rewrite this equation to reflect that. Now the equation states that the current over some length crossed with a magnetic field equals the force on that charge. Now we'll look at our motor again. Remember that we're attempting to understand the force causing our wire to spin. We have the current, represented in red, flowing through a length of wire that is passing through a magnetic field, in purple. In order to find the force on the wire, we need to look at that last equation, a current crossed with a magnetic field. So what does a cross product do? Let's look at the general form. Here, U crossed with V yields this matrix, where I, J, and K represent the regions of a 3-dimensional plane. Each value in the vectors U and V are places in the matrix corresponding to their directions in the plane. Evaluating the matrix leaves us with this expression, where each region is applied to a 2x2 matrix of values from U and V. Let's go back to our motor. As we can see, we have 2 vectors in 2 directions. Our current is moving in one direction, and our magnetic field is moving in the other. If we establish a 3-dimensional plane around the motor, we can tell that the current is moving in the x-hat direction, and the magnetic field is moving in the y-hat direction. Now let's go back to our equation. The current through a length of conductor crossed with the magnetic field leaves us with this matrix. Evaluating this matrix finds us with 0 in the x direction, 0 in the y direction, and our force winds up going entirely in the z direction. We can now rewrite our force equation in this way. So now, taking what we've learned so far, we can determine that if the current is flowing through a magnetic field that is 90 degrees parallel, our force is in this direction, causing the wire to spin clockwise, as we can see here. It is entirely possible for the wire to spin faster, but it has to be bent in just the right way to encounter a very small amount of friction on the battery. So now that we've built the standard style motor, let's look at some different shapes for our wire. The next wire bend was like this, very similar to the first motor, but now with only one vertical wire for the current to pass through. The math is still the same, however. As the current moves through the wire and passes through the magnetic field, according to Lorentz Force, the force must be in the z direction. And so it is. Now we change things up a bit. Instead of going with another right angle wire, how about a spiral? While the geometry might be completely different, there's nothing different about the physics. As the current passes through the wire away from the screen, it crosses the magnetic field in purple, and Lorentz law tells us that the force must be down on the wire at every point on the wire. This downward force causes the wire to spin in a counterclockwise direction, as can be seen here. This is personally my favorite design. And now for something perhaps a bit more practical. No more loops of wire for us. Now we make some things besides a wire spin. In this case, a screw. Now the circuit is completed when the wire that we hold to the positive terminal is connected to the magnet that is on the bottom end of the screw. The screw itself is held in place to the negative terminal by the magnet. Now, since the wire is not our focus anymore, we'll have to look at the only moving part left, the screw. As the current passes from the wire through the magnet and up into the screw, it encounters the magnetic field from the magnet on the right-hand side of the screw. We call on Lorentz again to tell us that the force created at this point will cause the screw to turn counterclockwise. And the same thing will happen on the other side of the screw, where the magnetic field is moving in the other direction. This combination of forces, in addition to the point of the screw being the only contact to provide friction other than the motor itself, causes the screw to spin at great speeds, as we can see here. It's difficult to see because of the quality of the camera, but you can make out that it is spinning. And since I was the one holding both the battery and the wire, I can assure you that it was spinning quite quickly, and even when I pulled the wire away, it continued to spin for some time. The entire point of this exercise has been to better understand how a magnetic field affects a current-carrying wire. I think it's fair to say that we've done that. Anytime a current flows 90 degrees parallel through a magnetic field, the force will always be exactly normal to the plane defined by that current and field. I'd like to thank you very much for watching and wish you a good day.